Okay, so we will move on to the questions now. Oh, I was talking about complexity, sorry. So when you're talking about complexity, you can have either arithmetic models, okay? Basically, you'll just supplement for turbulence by using some arithmetic relations. You can have one equation models, that is you solve one extra PDE. You can have two equation models. Two equation models are the most popular. I think if you've been studying aerospace, you might have been exposed to the idea of K epsilon and K omega models, right? So these are basically two equation models. That is, you solve for two parameters. Like for K epsilon, it's K epsilon, K and epsilon, very simple. And for K and omega, it's K omega. So basically, you just solve for two parameters instead of however many, one or something. But yeah, so these are two equation models. These are the most popular. Let's write it down. So it's definitely worthwhile to look at when and how you will be able to use these models, because when you're doing a simulation, it's even if you don't have a very good theoretical base of turbulence, you should still know what to use where. So K epsilon is typically better for external aerodynamics and K omega for like internal flows, right? And there is another category which is six equation model. So these models are not exactly set in stone or something. Even if you were to go ahead and study and make a model which approximate turbulence may be a four equation or a three equation or however many equations you want, then also that's all admissible as long as you're able to predict all the features that you want to predict fairly accurately. I mean, that's the objective of using models, right? This is Reynolds stress. Right, so now we'll move to the questions. There's a lot to be discussed in turbulence. Actually, it's a very interesting subject. So we'll see if we have time after that, and then I'll maybe speak a little bit more about it. Right. Okay. So this is we come on to the questions. According to the Prandtl's mixing length model, in a flow where the only significant mean velocity gradient is du by dy, the Reynolds stress is proportional to. So we're talking about the mixing length model. It's a very simple model and something you must have seen in your lecture notes or in your lectures. So basically, the Reynolds stress is then proportional to this value. That is, since we have only one, basically Reynolds stress in general are proportional on the velocity gradients. And here we are told that the only significant mean velocity gradient is du by dy. So it is actually proportional to the square of du by dy, which I can see over here. And yeah, that makes sense to me. One important thing is that the difference between option B and option D, that is, you can see in option D, we are essentially squaring the magnitude of the, I'm sorry if you can't see it. The size. Yeah, yeah, okay. Hmm. So like in option D, basically you are just erasing the significance of the sign. Sign significance erased. So that's not what we want. We do want some indication regarding the sign of the gradient, whether it's negative or positive. So yeah, significance removed. So our correct answer over here is B. I think you must have already guessed that from you've studied in the lectures already. Yeah. So then we'll move on to the next question. Okay. Mixing length model. Once again, we're talking about mixing length model. Is A incapable of describing flows with separation and recirculation? B can be applied to flows with separation and recirculation with some correction terms. C capable of predicting thin shear layers such as jets, mixing layers, weights and boundaries. So thin shear layers is an important terminology over here. Needs very fine grid resolution. So I would like it if you could maybe write your guesses in the chat box, Shipra and Vitul. I think it'll be a good exercise for you. So yeah, I mean whatever you think from you studied in the lectures. So yeah, just let me know. I'll just give you a hint. There are two options that are right in this particular case. Like, I'm gonna wait for like approximately 1 minute. If you want to answer, then go ahead. Yeah. Okay, so I'll move on. So there are two correct answers to this, as I spoke about it. So it is incapable of describing flows with separation and recirculation. So we need to once again understand and realize the importance that mixing length model is essentially a very simple model. Its work is to only like get us an okay answer for some cases, and its advantage is that it's very cheap. So definitely D is not the right option, because if it needs very fine grid resolution, it's not a cheap model. So this is wrong. And can be applied to flows with separation and recirculation with some correction terms. No, it can't. It can't. A mixing length model is just not capable of analyzing the separation and recirculation zones. It's a complex problem for it. And what it can be used for is that it can be used for jets, mixing layers, wakes, and boundaryless. It's basically, like as the name suggests, it's a mixing length model. So it's good for like basically just understanding what is happening at the boundary layers and how mixing is going on in that case. Yeah, yeah. So we have that answer over here. Then moving on to the next question. Just let me know if it's not visible. I think the font is too small. Trying to make it larger, but yeah. Okay, so the term Sij. So what's Sij? It's the stress tensor multiplied with itself. Found in the mean flow kinetic energy equation of K epsilon. So we're talking about K epsilon equation model is related to. So we're looking at the two equation model K epsilon specifically, and there is a term which is related to Sij in there. Okay, so Sij dot Sij. So what I want to know is that what is this term basically telling me? So a lot of what we do when we are studying partial differential equations is to try to understand what each term is trying to tell me, right? So in this case, this is just the stress tensor, and this is a viscous stress tensor. There is no dash, like basically, for turbulence, like Reynolds averaging turbulence, like RANS plus turbulence models, what we basically do is that we just separate out the velocity into two parts. One is mean and one is fluctuating. So here we are not talking about the fluctuating terms. We're just talking about the mean, like basically the viscous stresses. We're talking about viscous stresses. So there are viscous stresses and there are turbulence stresses. Turbulence stresses are what we try to approximate. Viscous stresses is which we can pretty much get a good answer for already. So we're talking about turbulent or Reynolds stresses, whatever you want to call it. Essentially, whatever turbulent stresses or Reynolds stresses are there, they look very similar in terms of mathematical composition to your viscous stresses, which is Sij. So now we're being asked that what is this Sij term corresponding to? Let's see what all it tells us. Rate of destruction of mean kinetic flow energy. No, that's not right. Transport of mean flow. See, rate of destruction of mean flow kinetic energy would be like when we're talking about epsilon, right? Um, because basically this, okay, mean flow kinetic energy. That's not right anyway. Then transport of mean flow kinetic energy by Reynolds stresses. So this is not what we're talking about either, because transport is always related to convection. This is not related to convection. Rate of viscous dissipation, yeah, that sounds right. And transport of mean flow kinetic energy by convection. This is sorry, this is convection, and this is when convection with respect to u dash. Okay, rate of destruction, this is what is epsilon. So this is rate of viscous dissipation is what we are talking about in this case. So yeah, that's the right answer. Might be a little bit confusing. I can totally understand that. So a good idea I would say is to just sort of look at the equation and all of the terms and like that is given in your lectures as well. Sort of isolate each and every term and see what that means. So here the answer corresponds to the answer is rate of viscous dissipation because we're talking about Sij in here, which is like the mean stresses, right? Hmm. Okay, so then we are now the next question is the rate of dissipation of turbulent kinetic energy. Okay, yeah, no, I'm sorry. Yeah, this is for mean kinetic energy. Now we are talking about turbulent kinetic energy. So this was wrong by me. It's not epsilon. Okay, sorry. Yeah, in terms of mean kinetic energy, we're basically just talking. There is once again, I explained it to you, but I got confused on my own. So then there is a kinetic energy that is associated with the mean components, that is u square plus v square plus w square by 2. And there's a turbulent kinetic energy, TKE, which is this k that we solved for. That is u dash square plus v dash square plus w dash square by 2, right? So now we're talking about the mean flow kinetic energy. So when we are talking about the mean flow kinetic energy in this question, right? So what happens over there is that basically it is dissipated through viscosity, which is what this Sij term is doing over here. And there is some relation with the turbulent kinetic energy because basically this also is the production term for the turbulence kinetic energy. So, whatever is taken from the mean flow is given to the turbulent kinetic energy. So that's my understanding of it. And yeah, I would still suggest that you look at all the equations because this can be a bit confusing. Right. Now we're talking about rate of dissipation of turbulent kinetic energy per unit mass, E epsilon, is given by Sij. No, that's not right. That's not right either. It's also not right. Yeah, we're right over here. Okay. So these two might look similar, but then there's a difference wherein because we're using a dot over here and here it's plain square. So yeah, basically this is again viscous stresses. The small s corresponds to turbulent stresses. So since we're talking about epsilon, that is dissipation of turbulent kinetic energy, we're talking about turbulent stresses. So you see, like in the mean flow kinetic energy, the main dissipator is the viscous stresses and turbulent stresses or Reynolds stresses, which look very similar to your viscous stresses in terms of mathematical composition. That both of them are dependent upon the some form of gradient of velocity, etc. Those make their appearance over here, and you'll see that this is what appears in the equation for the dissipation term, and consequently this will be the production term for the epsilon. Okay, term for k, production term for e. Okay, so yeah, this is some more information related to the governing equations for turbulent kinetic energy and epsilon. I'm talking about k epsilon model, that is. Okay, yeah, fine. So the next question is, we use k and epsilon to define velocity scale and length scale representative of large scale turbulence as follows. So when we have our k and epsilon, we want to be able to sort of guess the size and velocity, etc., of whatever is going on over here. Like basically, what the largest scale turbulence might look like. So for very small scale turbulence, there is really no hard and fast limit to as to how small the um, scale of the you know of course there's a limit, but then basically the smallest eddies or the smallest turbulent features are like very very small, and we're not really very interested in that because such small scale turbulence structures, turbulent structures. They do help in mixing, and they have their own importance. But basically, from an engineering purpose, they're just not that interesting for us. So we generally stick to the guessing or approximating the large scale phenomena. So we see that, okay, it's asking us key what is the velocity scale and the length scale. That is the approximate velocity and size of these large scale phenomena. So this is also something related to more. This is a more theoretical thing. Since we're talking about modeling, therefore we'll have to sort of adjust and digest the fact that sometimes a lot of what we're talking about is up in the air. Since of course it's based on like solid work by solid researchers, but it's still modeling, so we're still approximating a lot of things. Anyway, that's not a problem. So the answer for this is this D. Basically, the velocity. You can see why, right? So if we have the turbulent kinetic energy, TKE, okay. So I'm defining it as essentially the velocity of the turbulent, that is the fluctuating velocity square. Okay, this is what I'm defining the K as. So definitely my velocity is going to be somewhat like, K raised to power half. And this is something which is more intuitive and logical. It sounds good to me. Uh, Whereas with respect to this thing, the length scale, we are typically looking at something like K half by under root of epsilon. Okay, so this is what's happening with us over here, and yeah, that's how you approximate the length scale for this case. Let me check once again. Think I'm wrong somewhere. Yeah, no. Yeah, this doesn't sound right to me. So, anyone else has any ideas on this? Because this is wrong. So, I marked the wrong option for you right now. So, you have any other idea from whatever you studied in the class? It's very clear. It's easy to guess what the scale for the velocity is. That's why all of the options have this half over here, which can be a bit misleading. But yeah, so what should the correct answer be? Does anyone have any ideas regarding that? It's related to whatever you must have studied in the class also. So, okay, so the right answer, I'm sorry, is actually C. It's C. Length scale is 3 by 2 by epsilon. So, in this case, because yeah, see, basically how I was able to understand that whatever answer I wrote was not right is because when I looked at this epsilon and when I was gravitating towards this answer because it looks familiar to me. So what happened in that case is that I recognized that this is not, see, if this is velocity and we're looking for length, so then what should this under root of epsilon be? It should be time inverse, right? Basically this. So that's not what epsilon does, because epsilon does have some like the dimensions of some length dimensions are also involved in the mix. So therefore we have to go with C. C is the right answer over here. This is again something that you can look at your notes and you will be able to justify it better in case it's not really clear. But basically these are all things that you'll have to learn. Okay, if you want some reasoning behind it, that's great. But sometimes we just won't be able to remember, so it's a good idea to just learn this out. Right. Okay. So eddy viscosity is proportional to. Now we are being talked about eddy viscosity. Mu. Let's just say 20. This is saying that how do I compute mu t? This is fairly standard in all of the models. You must have seen that. Yeah. it corresponds to k square. This is again something that I have learned, k square by epsilon. It's proportional to this. Sometimes you will have some or the other different types of constants multiplied with it. It says c mu, it might say b or something, whatever. C mu is something that is used for k epsilon, so therefore I remember. And yeah, that's the value of this is like basically something, a small value, something like this or something. And essentially, you just multiply it with the constant of proportionality, and then you get your eddy viscosity for the k epsilon model. For the k epsilon model. So you can see how this viscosity term basically couples your mean flow equations as well as your turbulent kinetic equations, turbulent equations. So a lot of questions on K epsilon. Okay, so from solution of K epsilon turbulence model, the Reynolds stresses may be calculated based on. So this is again a simple question. There's not too much confusion in this. So I would like it if you could answer this in the chat box. Then we'll define each of these things. It's okay, you can guess. There's no prize for being right. There's no punishment for being wrong. I've been giving you wrong answers, so it's fine. I mean, as long as you understand why they're wrong and all, it's fine. Just go ahead. Whatever you feel like answering, just say it. Oh, come on, Shipra Vitul. Just give me an answer. Any one answer is fine. Okay, so we'll see why that's wrong now. Right. So the answer for this is actually basically when you have Reynolds stresses. So once again, Reynolds stresses look similar to. Thanks for answering, Vitul. Though, thank you. Similar to your viscous stresses. Okay, that is they are dependent upon, stress is dependent upon S to whatever Sij, however you want to write it, is dependent upon velocity gradients. Okay, so this is our basic hypothesis with respect to Reynolds stresses uh, gradients. Okay, so this is our basic tenet, so to speak, of for our entire modeling, and that is based on this Boolean relationship. So essentially, what Boolean relationship says is exactly this, and then it gives us some more values to sort of approximate the Reynolds stresses. Okay, so now what is up with all of these other options? What are they? What do they mean? Since B is our right option, that is Boolean approximation is taken. So A is SGS, which is subgrid scale models. So what these models are? These models are related to LES, that is large eddy simulation. Okay. So what happens in here is that basically, I think in some detail this must have been spoken about. You you resolve, so to speak, resolve. That is, you use actual Navier-Stokes equation, big eddies, model small eddies. Okay. So this is what we talk about generally. So like if you have a flow structure, okay, here whatever, something's there, and there are some small turbulent structures over here, whatever. This small turbulent structures, okay, which is not that important for me. And then I have these great big turbulent structures over here. I don't want to make anything crossing and stuff. So yeah. So essentially, what the large eddy scale model does is that, let me get this on a bit careful, is that it numerically resolves for this. That is, I put a mesh over here and I numerically resolve all these big eddies. Meanwhile, the smaller eddies I model. So that modeling is done by using the SGS models, that are that is subgrid scale models. So you can see that these big eddies, they are sort of being captured by this mesh that I have just put. But these small eddies, they are smaller than even the grid. So those have to be modeled, and that modeling is done via SGS models. Okay. So I'm just going to go through these definitions because these are all like significant ideas. So yeah, SGS models for small eddies, right? So this is intricately related with large eddy simulation, right? And we were talking about K epsilon turbulence model. Then spatial filtering. Again, spatial filtering is also something related to a large eddy scale simulation. This is the spatial filter. Okay, that is whatever your size of resolution is. I mean, you can sort of imagine it like a net. Okay, and for example, you went fishing. Okay, and then you have a net in which like basically this is the size of your net hole. Okay, and your fishes of there are like two three, oh my god, just let me like draw a nicer fish. There's like a fish of this size, and then there are fish of this size, whatever, this small kind of fish. Okay, so when you put this net, you're only gonna catch this fish, right? But that doesn't mean that this size of fish doesn't exist. Okay, and for example, your objective of doing this fishing was to maybe get a count of how many fish there are in the pond. So, just fish them all out and throw them back or something. I don't know. It's not a great example, but it's an example. Right. So you have all of these big fish which you've counted, which you know for a fact that these fish exist. But then you know that some smaller fish also exist. You know that because that's how nature works. There are small fish in the pond as well, and you say that okay, I got 300 big fish, and on just like some assumptions and models, I'm gonna say there are 3,000 small fish. Might be a great idea, might not be a great idea. Maybe there are lesser, maybe there are more, but you just say that. Okay, so then basically this is your subgrid scale. Subgrid scale modeling, and this is what you've resolved resolution. Okay, you caught them, you know this exists for a fact. So the same way with eddies, that you know for a fact that these large eddies look in a certain way because you are using resolution over there. Meanwhile, you're using modeling for the smaller ones, right? And this is the spatial filter, which can be approximated to your net. You can just say it's like a net. Okay. D option is the Kolmogorov hypothesis. So this is basically just like a thought, not constantly thought experiment. This is a model, like this is an idea based on conjecture about where does the energy really go. Essentially, what they say is that cascades, that basically there are huge, large eddies. So these are dissipated by smaller eddies, which are further dissipated by smaller eddies, and which are further dissipated by smaller eddies, and the number of eddies keeps on increasing. Let me just do myself. Okay, which are further dissipated by smaller eddies, smaller eddies, until it just gets dissipated by the viscosity effect. So this is basically the Kolmogorov hypothesis. You'll hear something as energy cascading. And also there is some work and some conjecture which is based on the size of the smallest eddies. So just because this is something that pops in my head right now, might be a question in your brain as well, that why do we keep on applying Navier-Stokes equations, because when we are looking at such small phenomena, which is a very fair question, because you know that the Navier-Stokes equation is basically based on the assumption of continuum. So you're assuming that fluid is continuous all the time, but you know that at small scales, that is at microscopic scales, it's not continuous, it's made up of molecules. So, it's a very valid question to think about how small we can really go before our assumption of Navier-Stokes equation, the assumption of continuum just falls apart. And that's really valid. I mean, yeah, makes a person think. But then it has been noted by researchers that even the smallest eddy, that even this eddy that I'm drawing over here, which I'm just representing by dots, so these are all significantly larger than the molecules. Therefore, we're safe when we are using Navier-Stokes equation for this as well. Okay. So, I mean, there are certain cases in which your Navier-Stokes equation would not be a good idea, such as if you were in outer space or something, because at that point, if you're going to say that yes, my air is continuous, that really might not be a great idea, because the molecules might just be so far apart that yeah, the assumption of continuum just breaks down. Anyway, this is just some random ideas which I think are important and significant. So right, we'll move on to the next and last question we have over here. And right, so direct numerical simulation grid size scales with. So it's telling us okay, how does it scale? How many grid cells do you have to take for a particular Reynolds number? That's the question that is being posed over here. So the answers for this is again C, which is a rule of thumb basically. But I would like to take a minute and really, I would request you to appreciate this this relation. N is the number of grids. Okay, N is the number of grids, and talking about REN by 4. Okay, so you can really imagine that as your flow gets more and more turbulent, the number of cells that you need rise exponentially. They really do rise exponentially, right? So this is like around 2 point something, whatever this factor is. So basically, each time you are increasing your Reynolds number by a certain factor, you're going to increase the number of cells that you need by square of that factor. I mean, that's really something to think about. So you can imagine that, okay, for like small laminar, not laminar, but like for turbulent flows which are not very turbulent, that is the Reynolds number is not too high, we can get away with using a smaller number of cells. And mind you that even the smaller number will be considerable, it will be pretty huge. But when you're looking at something that is very turbulent, which is some, and I mean, it's important to realize that all flows that we see around ourselves, like I would say like probably 95% are turbulent, and they're highly turbulent. So when you're looking at something that is so turbulent and you really want to, capture it using DNS because that sounds like a good idea, it's totally not possible, not currently with the resources that we have, right? Because we cannot put so many cells into our domain, and even if we manage to do that, that also each small, like you, as you remember from the earlier weeks, that the time step is also related to the spatial step. That is, it's also related to the grid cell size. So when you're looking at such small cells, you're also looking at equally small time derivatives, sorry, time steps, and that's really something to think about. I mean, it will be so expensive, so expensive. So therefore, we go with turbulence modeling, and sometimes we even forego turbulence altogether. So really, the idea, like the question comes to the mind that when should I resort to turbulence modeling? When should I go ahead with it? When you should go with turbulence modeling whenever there is an importance of the turbulent mixing or separation or recirculation in your problem. When there is some importance of those factors, you have to go with the turbulence models. Okay, if by some reason you're not able to do that because of limitation in terms of computational facility, complexity in writing the code, or whatever reason you might have, it should be a good reason, then you should be aware of what you are missing out on. It's totally okay to under like scale down how much you want to solve. It's totally okay to ignore certain aspects of physics, but why you're ignoring them and what errors will that introduce in your solution. These are two things you should be very cognizant about. Those are important factors for us as engineers. The thing with direct numerical simulation is that it's elegant, it's beautiful, it helps you to really appreciate flow at a very elementary level. But yeah, it's very expensive. It's just too expensive, and it's not practical enough for engineers. It's a great tool for scientists, but as engineers, you will have to sometimes make certain decisions when you're looking at models or you're looking at whatever flow you're going to be analyzing, and you're going to have to make some hard and fast decisions regarding what you want to resolve versus what you don't want to resolve. And that should be based in physics, that should be based on understanding that when you are choosing to do that, you're also choosing to leave out a lot of the physics, and that can introduce errors. So really being cognizant of all of these things is important. Yeah, that's what I want to say. I mean, you should totally go through whatever the um, professor has given to you with respect to the lectures and all. Go through it, understand it, try to analyze whatever you've seen. But I think the most important takeaway from all of this is, as students, is to just understand and appreciate what we are doing when we are looking at turbulence and its model. It's really important. So yeah, I mean that's all I have to say for today. If you have anything to say to me, yeah, I mean go ahead. I'll just stop the recording so that you don't have to hear that later. But yeah.